Alright, so at the end of last time we talked about what I call the strain ellipsoid, and I guess to be more precise I should have called this the reciprocal strain ellipsoid, and how that kind of naturally leads us into talking about principal strains. Okay, so that's kind of a useful visualization for us. So this visualization is useful and it's of interest to us in the context of strain, because for certain rotations of the axes, the normal strains take on maximal values. And in fact, the maximal values are the eigenvalues of the strain tensor. Additionally, the eigenvectors define the directions to the coordinate axes where this occurs. And even further, in these directions there is only extension or contraction along these axes, meaning the tensor epsilon is diagonalized, and then there are no shearing strains in these particular directions. Lastly, because the strain tensor is real and positive, definite and symmetric, for any non-rigid deformation, we're guaranteed to have 3 real eigenvalues, although those eigenvalues may not be unique. Okay, so let me write a little bit of that down, and that'll get us into our discussion on these principal strains. Now, the derivation of it being shown to be an eigenvalue problem to determine principal strains, the maximal values of the reciprocal strain ellipsoid, is in our book, and they use a Lagrange multiplier technique and some additional analysis. And I typically leave that for students to write out as part of either a homework problem or maybe a quiz, take-home quiz type problem. And the reason why I do that is it's actually going to be a little bit easier when we get into talking about the stress tensor to go through and show that the stress tensor, for its eigenvalues, its principal values of stress, is an eigenvalue problem. It is a fair bit of math, and it just takes a little bit of time. It's fairly well laid out in the book, so I'm going to leave it to the discussion in the book. However, we need to make sure that we understand how we can do one of these eigenvalue problems to find principal strains. Then we're going to talk about a few other issues associated with them and related to the invariants of the strain tensor and so forth. So what I'm going to do next is I'm going to go through an example of finding eigenvalues and eigenvectors for effectively a 2x2 matrix. And so this class assumes that you've had a little bit of experience with linear algebra. If you've not, you'll still be okay in this class, but it would be helpful. And so what I have here is a strain tensor with its components 10 to 0, 2, minus 5, 0, 0, 0, and 8. And if you notice, this is not a fully populated matrix of components. It has some zeros in some certain spots. And that's because if we were to fully populate this matrix, the 3 by 3 fully general eigenvalue problem is a little bit hard to work. And typically what I will do is I will ask a question very similar to this on a quiz, so that I know that everybody can find principal values and eigenvectors for this state of what we would call generalized plane strain. Now these are unitless, and I'm just making up some numbers. Typical strain values, these might be times 10 to the minus 3 or 10 to the minus 4 for metals. But it doesn't have to be a small strain tensor. It could be finite deformations as well. Well, the goal in looking at this is we have to remember that this particular representation of the strain tensor is for a particular coordinate system. So somewhere in our body at this particular point we've identified an XYZ coordinate system, and these values are the strains in the epsilon x, epsilon y, and epsilon z system, and the shearing strain in the XY system, or along the diagonal epsilon 1, 1, epsilon 2, 2, and epsilon 3, 3, in the tensorial shearing strain epsilon 1, 2. The other tensorial shearing strains epsilon 2, 3, and epsilon 1, 3 are equal to 0 in this particular example. Now the goal is to take this state of strain and rotate its coordinate system such that we diagonalize the components of the strain tensor. That we transform these components according to our tensor transformation rules in such a way that we have zeros everywhere except along the diagonal. And once we find those values along the diagonal, then this is those are the principal strains. Now, when we were to do if we were to do the full 3x3 matrix, there are certain techniques that you could employ to help you figure out, at least try to get 1 0 in there. And I kind of liken it to solving a Rubik's Cube. You work on this thing and you get one side and you get things lined up just the right way, but the other sides are all out of whack. And so you keep rotating this thing and you keep doing transformations until you get things to line up for the entire matrix. Now, that full 3x3 matrix, there's some techniques you can do, but really at this point in history, it's not worth a whole lot of time trying to do this by hand, in my opinion. You have tools such as MATLAB. You can go on the web and you can do eigenvalue calculators online. There are websites that will do that for you. So we're going to take a look at the special state of strain called generalized plane strain with these zeros in here. Now, since there are zeros in these two positions, these 4 positions here, I can immediately look at this and I can determine that 8 is going to be an eigenvalue of this matrix. So I'm going to call the eigenvalues lambda. So lambda is equal to 8. And the eigenvector associated with that one is 0, 0, 1. If we think of this being in the x, y, z coordinate system, this 8 units is completely in the z direction, and so that would be 0, 0, 1. So now we can immediately reduce this problem down to a 2x2 problem. And to state the eigenvalue problem, we can say something like, in general, what we're trying to do is we're trying to solve the problem epsilon minus lambda I times n is equal to 0, where n is a unit vector. Actually, this is the 0 vector right here, where n is the 0 vector, and where n is not the 0 vector, n is a unit vector. 0 vector is over here. And so what that means is, in order for this equation to equal to the 0 vector, this has to be the 0 tensor over here on the left-hand side. Well, we can develop the characteristic equation, and we'll do that in a moment. But for the reduced problem, for the 2x2 problem, basically what we're going to do is we're going to take a look at this reduced matrix 10, 2, 2, minus 5. We're going to subtract lambda, lambda being the eigenvalues, and we can even put a subscript on this one. This is maybe our first eigenvalue that we've identified. And then we have the identity matrix, or the identity tensor, in this position. And so we can have this new matrix 10 minus lambda, 2, 2, minus 5 minus lambda. Now we can develop what's called the characteristic equation by taking the determinant of this matrix. And if we know that this has to be the 0 tensor, of course the determinant of the 0 tensor has got to be 0. So the determinant of that matrix, I'll write it one more time, the determinant of that has to be equal to 0. To evaluate a 2x2 determinant, we just take these two terms and multiply them together. So we're going to have 10 minus lambda minus 5 minus lambda. And then we take these two terms and subtract those multiplied together. So we'd have minus 4 right here. So we're going to do a little bit of algebra. The left-hand side, we're going to have minus 50. We're going to have minus, I guess it'd be plus 5 lambda. We're going to have a minus 10 lambda. And then we're going to have a plus lambda squared, and then we have that minus 4 right there, equal to 0. Let's make a little bit of room. Okay, so now let's do a little bit of algebra on this characteristic equation. We're going to lead off with the lambda term. So we have lambda squared. It looks like we're going to have a total of a minus 5 lambda and then a minus 54 equal to 0. What we're trying to do is we're trying to find the roots of this equation for lambda, and we can very easily do that with the quadratic formula. So our other two roots, we'll call them 2 and 3, are given by, if we write it in standard form, minus b plus or minus the square root of b squared minus 4ac all over 2a. And in this particular case, that's going to be plus 5 plus or minus the square root of 25 minus 4 times 1 times minus 54 all over 2 times 1. And if I put that in my calculator, it's going to be 5 plus or minus 15.5242. I'm going to go ahead and carry some extra significant digits for now, divided by 2. And so one of the roots is going to be 10.2621. The other root is going to be minus 5.2621. And I notice that these are real roots. They're not going to be imaginary roots. If you end up with an imaginary number in this, or a complex number, then something's gone wrong somewhere. Now that we found those, we need to figure out the eigenvectors associated with each one of those eigenvalues. Okay, so what we do is we go back to our equation right here. We're going to try to find the associated n that goes with a particular eigenvector, particular eigenvalue. So looking at my matrix, 10 minus lambda, we'll do lambda 2, 10.2621. We've got 2, 2, and then minus 5 minus lambda. Is associated with a two-dimensional vector that has two components, n1 and n2, and that has to be equal to the 0 vector over here on the right-hand side. So this is true right here. And I know that n1 and n2 cannot be both equal to 0. Now it looks like I have a system of equations, but it turns out these equations are not linearly independent. I need to find the ratio of one of these components for n in terms of the other. So if I take this column and multiply it by this first row, I'm going to get minus 0.2621 n1 plus 2 n2 equal to 0. And I will get the ratio of n1 being equal to minus 2 divided by minus 0.2621 times n2. I can do the same thing for the second row, but I would not get anything different than what I have right here. If you want to make sure that you haven't made mistakes, you can go ahead and do that. Now I need to find an eigenvector, and in order to do that, I'm just going to assume that this component n2 is equal to 1. And if n2 is equal to 1, I do the math, then it'll turn out that n1 is equal to 7.6307. So now that means I have a vector that is component 7.6307 and 1. Now the third component will be 0, but we're not just doing the 2 by 2 problem right now. Now when I look at this vector, this is not a unit vector. And while that is an eigenvector, for our purposes, we want to convert that over into a unit vector. So the way that we do that is we divide these terms by the magnitude. Let me make some more room. Okay, so I need to find the magnitude of this vector. Okay. To do that, I'm going to take the square root of the sum of the squares and divide this whole thing by the scalar 7.3607 squared plus 1 squared. And when I do that, I end up with 0.9915 and 0.1299. Now the magnitude of that should be 1. Let me just check my math. Let me get my calculator out, and I'll just put this in here real quick. 0.9915 squared, 0.1299 squared. I'm going to add them together, and I'm going to take the square root, and that's pretty darn close to 1. I got 0.99997 on my calculator, so there's a little bit of rounding. So that's why I like to keep a little bit of extra significant digits in here, because of the rounding issues. Alright, so the two-dimensional eigenvector looks like that. The fully three-dimensional eigenvector is going to have that third component in it, which is going to be 0. There is no component in the z direction or the 3 direction because we had already diagonalized that term. It came that way in the problem. All right, let me make a little bit more room again. And we'll do the exact same thing for the third or the last eigenvalue. We're going to set up our problem like 10 minus a negative, so that's going to be plus 5.2621. 2, we have 2, and then we're going to have minus 5 minus 5.2621. And now this is a different n1 and n2 than I have right here. But in the end, that has to be equal to the 0 vector. So if I look at my first one, it looks like I'm going to have this column multiplied by this row. And it's a straight symbol there. So it's going to be 15.2621 n1 plus 2n2 is equal to 0. So if I solve for n1, that's going to be minus 2 divided by 15.2621 n2. We're going to take n1 to be equal to 1. Sorry, we're going to take n2 equal to 1. And then we'll be able to solve for n1. And in this case, when I do that math, I got minus 0.1310 n2. Or if I take that equal 1, then I'll have that. That's a 1, 3. Let me fix that. Alright, so now I have a 2 by 2, or excuse me, a two-dimensional vector that has minus 0.1310 in 1. I need to find the magnitude of that. So I'm going to take this and I'm going to divide it by the square root of the sum of the squares, minus 0.1310 quantity squared plus 1 squared. And when I do that, I get, for the two-dimensional vector, 0.1299 and 0.9915. Alright, so let me write this down. Try to make a little bit more room again. We had minus 0.1299, 0.9915, and then the third one would be 0 when we write the fully three-dimensional vector. Okay, so we have these three vectors now. And if you know about linear algebra, eigenvectors must be perpendicular to one another. And we know how to assess perpendicularity. If their dot product is equal to 0, then these vectors are perpendicular. So if we were to take 0, 0, 1 and dot it with 0.9915, 0.1299, 0, we do indeed get 0. If we were to take 0, 0, 1 and dot it with the other one, minus 0.1299, 0.9915, 0, indeed, again, we get 0. So those are perpendicular. And lastly, if we were to take the other two, 0.9915, 0.1299, 0, and dot it with minus 0.1299, 0.9915, 0. Then in that case, we would also get 0. So all three are perpendicular. So that's a good check to see if you have done everything correctly. If you got anything that's not perpendicular, either you have a little bit of rounding or there's a more major mistake somewhere. Now we can also provide an interpretation of the directions for these eigenvectors. Let me do this on a new page. When we started off defining our strain tensor, we said we had a particular coordinate system that we must have been looking at. And for our convenience, well, for my convenience anyway, let's say that it was the x and y coordinate system. And we're looking at it this way, and we're in the plane of x and y. So the direction off this way would be a vector that would have components of 1, 0, 0 for a unit vector. But what we have for this lambda 2 eigenvector is a direction that's mainly in the x direction, but goes up a little bit in the y. So maybe I'm going to, maybe exaggerate this a little bit. It's a very small angle, but this direction in the xyz coordinate system has components 0.9915, 0.1299, and 0. So this dimension for this triangle is 0.9915, and this dimension up this way is 0.1299. That means I can find the angle from the x-axis at which this new direction is pointing. So I can say that the tangent of theta is equal to the opposite over the adjacent, and I'm expecting it to be a pretty small angle. If I compute that number, it's 0.1310, and if I put that into my calculator, if I did that right, I got an angle of 7.463 degrees. Let me just check that real quick. Make sure I had my calculator in degrees and not radians. Yep, 7.464 degrees, 7.463 degrees. And so that is the angle that makes. Now the other one I know is going to be perpendicular to it. The rotation in the plane makes this problem kind of easy. And this angle right here will be the same angle, the same 7-degree angle. The two red lines are perpendicular to one another, and they're both perpendicular to the third one that points in the z direction out of the page at us. Okay, so now we have a new triad, and if we want, we can re-reference our strain tensor components to the principal strain directions. Well, let's take a look in more detail at our characteristic equation. In general, for any eigenvalue problem, we can write the characteristic equation for a 3x3 set of components as lambda cubed minus some value j1 lambda squared plus j2 lambda minus j3 equal to 0. Now, some books will write the characteristic equation with alternating signs, as I have done here. Other books may write the characteristic equation without the alternating signs, and so you have to be a little bit careful of what you define for these j1, j2, and j3 terms. Some books may have one of these being negative and the other one being positive. But these are well-known values. In this characteristic equation, since we need to end up with the exact same eigenvalues no matter what coordinate system we start with, these coefficients in this characteristic equation are going to have to be invariant to coordinate transformation. And in fact, one of the properties of tensors is that we have, second-order tensors, we have 3 invariants. A first-order tensor, a vector, has 2 invariants, magnitude and direction. A zero-order tensor, which is a scalar, has 1 invariant, well, its scalar value. And you can generalize this. If you have an nth-order tensor, then I guess you're going to have n plus 1 invariants. Okay, so I'm going to define these now. J1 is the trace of the strain tensor. And what the trace is the sum of the diagonal terms. In any coordinate system, we can add the 3 diagonal components. We can represent this in index notation as Kronecker delta ij, epsilon ij, or using the contraction operation of the Kronecker delta, then it's just epsilon ii. Of course, if we diagonalize it, it's the sum of the 3 eigenvalues. The second invariant of the strain tensor can be determined as the determinants of the 3 cofactor matrices added together. So let's write it this way: summation of the determinant of the cofactor matrices. How you determine the cofactor matrices is you strike a column and a row out, and then you find the determinant of the 2x2 things that are left. So, for example, if we had the full 3D, fully populated 3x3 strain tensor, if we struck out one of the rows and columns, we would be left with a 2x2 matrix. We would have these values. And then the next one, we need to get all the cofactor matrices. See, I'm moving from right to the left. I will get this. And then lastly, if I struck out the first row and the first column and the last row, then this would be my cofactor matrix. First row in the first column in this particular case. Okay. And we can express this as epsilon 1,1 times epsilon 2,2 plus epsilon 1,1 epsilon 3,3 plus epsilon 2,2 epsilon 3,3 minus epsilon 1,2 squared minus epsilon 1,3 squared minus epsilon 2,3 squared. It's not terribly important, in my opinion, that you memorize these, but you should know where to look to find them. And of course then we have an expression that we can write in terms of the principal strains or the eigenvalues. In the case where we have diagonalized the strain tensor, we can use this expression to find J2. That makes sense if these off-diagonal terms are equal to 0. Lastly, the third invariant of the strain tensor is simply determined by finding the determinant of the strain tensor. And in terms of principal strains, it's the product of lambda 1, lambda 2, and lambda 3. Okay, so we'll work with invariants a little bit more when we talk about stresses, but for now, might be a good idea just to brush up a little bit more on linear algebra. A couple more terms that we can talk about as we're in this section. One's called the volumetric strain. We can define that in a similar way to what we have defined our magnification factor. You can have 1/2 d script v by d regular v squared minus 1, where d script v is the volume in the new configuration for our point, rounder point, the neighborhood of that, and d regular v is the volume in the original configuration. If we are in principal axes, the magnification ratio along a principal axis, say the 1 axis, can be determined based on the eigenvalue in this way. And so the volume then would be the multiplication of the 3 values, or the volume ratio term right here, can be pretty quickly determined. And this term right here is actually squared. All right. So this term squared would be 1 plus 2 lambda 1 times 1 plus 2 lambda 2 times 1 plus 2 lambda 3. Now we can do some manipulation with this and then write the volumetric strain in terms of the invariants that we just discussed. In this case, it's J1 plus 2J2 plus 4J3. Remember, these are dimensionless quantities for the strains that we're talking about. Now, if we neglect higher order terms and only look at terms that are first order in epsilon, then we're just left with the first invariant. And in that case, the volumetric strain is just equal to J1. It's equal to, say, epsilon kk, where k is a dummy index. It's equal to epsilon 1,1 plus epsilon 2,2 plus epsilon 3,3. And if there is no volumetric strain, okay, then the strain tensor is equal to 0. But what that means is, if there's no volumetric strain, then volume is conserved. And this is a pretty typical assumption for metal plasticity. We can even express this in terms of gradients of the displacement vector. So with the strains being equal to partial of u with respect to x sub I, and we add these three together, and we have a differential equation that must be satisfied in order for us to have the conservation of volume. We can talk about the mean strain tensor and the deviatoric strain tensor. And the basis for this is that any symmetric tensor can always be split into two parts. A mean and a deviator, where the mean is equal to the trace over 3, that's Kronecker delta ij, and the deviatoric tensor is simply everything else that's left. It's that tensor minus the mean tensor. This is also used a lot in metal plasticity. And each of these two tensors, or second order tensors, they can have their own invariants, as we've seen defined previously. We can compute the invariants, the j, for each of these two tensors. In some cases, some of these may vanish the way they're set up. One of them will have some terms that will go away. But we can define things just like that. And again, we'll talk about this more when we get into stresses. It's probably a little bit more meaningful when we talk about stresses with the mean and deviator, because those have direct applications in metal plasticity for stresses, whereas they're not usually used very much for yield criteria for metals in terms of strain. Now we have another term we can talk about, and that's called the octahedral strain. And for that, I'm trying to draw a cube. And the edges of this cube are aligned with the principal strain directions. And on that cube, aligned with the principal strain directions, let's write that down. If I were to take a plane that's formed by going equally along each of those principal strain directions, look something like this. In this picture, if I were to draw a coordinate system, maybe one like this, then the plane would look something like this. And these intercepts would all have equal distances. Now it turns out that if you have an equal distance intercept, then the normal to that surface that I just drew would have components of 1 over the square root of 3 for each of these. So this is a unit normal. If we were to do the sum of the square root, the sum of the squares, and then take the square root, we would have a magnitude of 1. The normal strain on that plane off in that direction, which we could find by evaluating our epsilon ij, ni, and j, in Ni in J. We can find that to be lambda 1 plus lambda 2 plus lambda 3 divided by 3. That's the mean strain. And on that plane, that'll also be the octahedral strain. That's the extensional strain on that plane. We also have a shearing strain that exists on that plane. I'll write the formula down. We'll again get into more detail when we talk about stresses. The octahedral shearing strain magnitude is 2/3 square root of, in terms of the principal strains, lambda 1 minus lambda 2 quantity squared plus lambda 1 minus lambda 3 quantity squared plus lambda 2 minus lambda 3 quantity squared, square root of that. If we look at that term, these are differences between principal strains. Interpretation of that is these are various diameters of Moore's circle if we were to plot this particular state of strain on a Moore's circle. Okay, so it's related to sort of an average type of, or a weighted type of maximum in plane shearing strain for each of the three particular local maxima shearing strains. Again, we'll get into more details when we get into stress. All right, one last, or maybe two last things we need to talk about. And the first thing is that we have defined our Green-St. Venant strain tensor as follows. And we've been looking at finite deformations so far. And in those finite deformations, we have this term. It's actually three terms when we expand out the index notation. And those terms, though, are multiplied by each other, so they're higher order than the first two terms. Now, if these were numbers like 5 or 10, then we must include these terms. But if these are numbers like 1,000 micro or something like that, 0.001, then when we multiply really small numbers together, these become pretty insignificant compared to the leading terms. So what we're going to do at this point, we may go back, and if we look at hyperelasticity, we'll have to go back to finite deformations. But for right now, we're going to take these higher order terms and make them approximately 0 for small deformations. So the small deformation strain tensor will look like partial of ui with respect to xj plus the partial of uj with respect to xi. Or if we put the 2 to the other side, we have a half times partial of ui with respect to xj plus the partial of uj with respect to xi. It's still symmetric. We still have all of those eigenvalues and eigenvectors that we can have, but now we've just thrown out those higher order terms. Use our comma notation as well. Oops. And if you've taken a class, probably beyond your first class, mechanics materials, taken a class that deals with stress and strain analysis, you may have started with this definition of the strain tensor. Now, it's also interesting to note that if we had the Almansi strain tensor, it would reduce down to the exact same thing as what we have here. So what we're saying is that if we look at our initial configuration and our final configuration, there's not a whole lot of difference but there's enough to be measurable, at least to the first order terms. The higher order terms would go away, and it doesn't really matter if we base our strains on the initial configuration or the final configuration. With that, the last thing we need to talk about is something called compatibility conditions. Now these compatibility conditions we're going to discuss in the form of the small strain tensor. The math is a little bit easier for us to work with, but these also hold for finite deformations as well. Now the underlying premise here is that we have three components of displacement, U1, U2, and U3, but we end up being able to compute 6 unique components of strain. Because the strain tensor is symmetric, we're going to have epsilon 1, 1, epsilon 2, 2, epsilon 3, 3, and then the shearing strains in the tensor form, epsilon 1, 2, epsilon 1, 3, and epsilon 2, 3. There has to be some connection among these displacement components so that this situation can happen. Now the way to see this is first taking one of these, say for example epsilon 1, 1, we know that that would be equal to the partial derivative of u1 with respect to x1. Epsilon 2, 2, likewise, is partial derivative of u2 with respect to x2. Now let's take a look at taking the second derivative of these with respect to x2. So in this case we would get the third partial derivative of u1 with respect to x1 and x2 twice. And on this one we would get second partial of epsilon 2, 2 with respect to x1 twice would be the third partial of u2 with respect to x1 twice and x2. Okay, let's keep that in mind for a moment. Let's look at the shearing strain, and I'm going to write it this way, 2 epsilon 1, 2. Shearing strain 2 epsilon 1, 2 can be found by partial derivative of u1 with respect to x2 plus the partial derivative of u2 with respect to x1. Now let's take the second partial derivative of that with respect to x1 and x2. We would have the third partial derivative of u1 with respect to x1 and x2 twice, plus the third partial derivative of u2 with respect to x1 twice and x2. Okay, let me make a little bit of room here. And so if we look at this, okay, we've got 2 second partials of epsilon 1, 2 with respect to x1 and x2. We have a third partial of u1 with respect to x1 and x2 twice. Okay, that's this term right here. This would be the same as the second partial derivative of epsilon 1, 1 with respect to x2 twice. And this component, third partial of u2 with respect to x1 twice and x2, would be second partial of epsilon 2, 2 with respect to x1 twice. Okay, and then likewise, we have 2 more additional relations. 2 second partial of epsilon 1, 3. Some people write this in terms of the engineering shearing strain. The mixed partial with x1 and x3, is equal to the second partial of epsilon 1, 1 with respect to 3 twice, plus second partial of epsilon 3, 3 with respect to x2, with respect to x1 twice. And, let me check, make sure I didn't get off on the wrong line here. I think that one's okay. And then the next one, to second partial of epsilon 2, 3 with respect to x2 and x3 is equal to the second partial of epsilon 2, 2 with respect to x3 twice, plus the second partial of epsilon 3, 3 with respect to x2 twice. Now there are 3 additional relationships, which I usually ask to have derived as homework, but I'll write them down. Maybe I'll just write one of them down for brevity. And the second partial derivative of epsilon 1, 1 with respect to x2 and x3 plus second partial derivative of epsilon 2, 3 with respect to x1 twice is equal to second partial derivative of epsilon 1, 3 with respect to x1 and x2 plus second partial derivative of epsilon 1, 2 with respect to x1 and x3. And let me just do this and 2 others that are similar. You can do a replacement on indices. You can cycle through the indices and see what those terms would look like. Now there's a more compact way to write this in index notation. Epsilon mn, comma ij, plus epsilon ij, comma mn is equal to epsilon im, comma jn, plus epsilon jn, comma im. These are known as the compatibility equations. Now, contained within this set of equations are these 6 equations that I just mentioned. There are also some things like 1 is equal to 1 that pops out with certain selections of these subscripts. Now, what the compatibility equations mean are the same things that we've talked about when we talked about the fundamental assumptions of continuum mechanics. If we have compatible deformations, then we do not have any fracturing of our material in that region, no splitting, no 2 points coalescing into 1 point. We don't have any penetration of the material into itself. Okay, so we can't break it apart. 2 points, 1 point can't split into 2, and 2 points cannot coalesce to 1. Means that we have a 1-to-1 correspondence in our original body and our deformed body. The deformation fields are admissible, single valued, and so forth. Well, we could probably spend an entire semester just talking about the strain tensor. And this being a class in elasticity, we need to know enough about the strain tensor to understand what's going on. We also have to have some time to talk about the stress tensor, and then we need to talk about how the stress and strain tensor are related through our elastic material relations. And then hopefully we'll get a chance to solve some problems, and we will. But I'm going to try to pick up the pace a little bit when we talk about the stress tensor. I will probably throw in a few more interstitial videos that aren't completely necessary to watch to be successful in the class, but can provide additional background information. Of course, again, if you've had a class in continuum mechanics, then a lot of this should be reviewed, and hopefully, if If it didn't make sense then, maybe it'll make more sense now, and vice versa. If you take this class before you take a class in continuum mechanics, maybe this will help make some of the continuum mechanics make more sense.